Hello everyone, today is day 8 of solving a LeetCode problem every day, and today we will be solving valid Sudoku. So this is another medium problem. So it asks, determine if a 9 by 9 Sudoku board is valid. Only the filled cells need to be validated according to the following rules. Each row must contain the digits 1 to 9 without repetition, so each row can't have any repeating digits. Then each column must contain the digits 1 to 9 without repetition, so every single column can't have any repeating elements. Then each of the 9 3 by 3 subboxes of the grid must contain the digits 1 to 9 without repetition. So each of these boxes that you guys see, there can't be any repeating elements in these boxes. So notes, a Sudoku board partially filled could be valid, but it is not necessarily solvable. Only the filled cells need to be validated according to the mentioned rules. So some of the constraints is the board length is always going to be 9. Then each individual row is always going to be of length 9 also. Then every single element in the board is going to be a digit from 1 to 9 or a period. So we don't have to worry about getting any digits that are not valid. So yeah, let's jump straight into the solution. So let's say we're hypothetically given a Sudoku board such as this one. I'm going to divide this algorithm into 3 steps. First of all, we want to make sure that the rows are valid, so there are no duplicate integers in each row. Second thing is we want to check each column to make sure they contain no duplicates. Then lastly, we want to check the 3 by 3 squares to make sure that those have no duplicates. Cool, so let's start with number 1. How do we check each row to make sure that they don't have duplicates? The way we're going to check to make sure that each row has no duplicates is by using a set. So what we're going to do is we're going to iterate through each value in each row and append them to the set. So in this case, the set would look like 5, 3, and 7, since we're not going to add any of the empty spaces. Now let's say there was a 3 here inside the row. So now we see that there's a duplicate since there are 2 3s. How this algorithm is going to work is we're going to first check if the element is in the set before adding it. So we start with 5. We want to check if 5 is in the set. It's not, so we add it. We're on a 3. We check if 3 is in the set. It's not, so we add it. Then we go to 7. We see that 7 is not in the set, so we add it. Now lastly, we're at 3. We see that 3 is already in the set over here. So what we're going to do is return false, since as we know, each row cannot contain any duplicates. So we finished step 1. Now what is step 2? We have to check that each of the columns have no duplicates. So the way we're going to do this is very similar to what we did in step 1. But instead of initializing a set, we're going to actually initialize a dictionary. And this dictionary is going to hold a bunch of keys where each key is going to be the column number. So we have 0, 1, 2, 3, so on and so forth. Then each value for those keys is going to be a set. And in this set is going to contain all the values within that column. So it's going to be this exact same algorithm as what we did in step 1. Before adding any value to the set, we're going to first check if it's in the set. And if it's in the set, we return false. The reason why we're using a dictionary instead of just a set this time is because when we're looping through the Sudoku board, we're going to loop row by row. And what this means is we're going to have to pretty much process the whole board row by row instead of column by column. So we have to hold pretty much a set for each column, and then we have to keep updating it every row iteration. So that was step 2. Now how do we figure out if there are any duplicates in each individual 3 by 3 square? So what we're going to do is going to be extremely similar to what we did in step 2. We're going to initialize 2 variables, x and y. And x is going to equal to row floor division by 3, and y is going to equal to the column floor division by 3. So the reason why we're doing this is we're going to store all these keys as tuples, where the x value is the current, I guess, row square we're at, and the y value is the current column square that we're at. And what I mean by that is we can look at these squares as actually only being index 0, 1, and 2. Since we have a square here at index 0, a square here at index 1, then a square here at index 2. And we can look at this the same way vertically. So now if we grab these actual column indexes, as you can notice, if you divide 8 by 3 and you use the floor division operator, you would get 2. If you divide 7 by 3, you would get 2. If you divide 6 by 3, you would get 2 again. Now if you divide 5 by 3, 4 by 3, or 3 by 3, you would get 1. And then the same thing with 2, 1, and 0. If you divide any of those by 3, you would get 0. Now it's going to be the exact same thing with each row. Whatever row we're at, if we floor divide it by 3, we're going to get the corresponding index that we need for the specific square. So pretty much what we're going to be doing here is constructing sets for each one of these squares, and it's going to be the same algorithm as before. We check if the value is currently in the set before adding it, and if it is, we return false. Otherwise, we just add it into the set. Cool, so we went through the general idea of the solution, so now let's code it up. So let's get straight into the code. We're going to begin by initializing 2 dictionaries, our square dictionary and our column dictionary. These are both going to be initialized to default dictionaries where the default value is going to be a set. We are then going to loop through every single row on the board. We're then going to initialize our row set to just be a set. We're then going to loop through each column within the specific row that we're in. If the current element is already in the set, then we just want to return false. Otherwise, we then check if it's not a period, and if it's not a period, then we can just go ahead and add it into our set. Next, we're going to loop through all the columns on the board again. If the current element that we're at is a period, then we just want to continue. We then want to make our x and y calculations. So as I said earlier, we do that by performing floor division on the current row and current column, and we do it by 3. We then check if the current element is already in its corresponding set in the column dictionary, and if it is, we return false. We then do the same thing with the square dictionary. And finally, if none of these conditions are true, we're just going to go ahead and add the current element to its corresponding set in the column dictionary and square dictionary. I made a little typo here. These are supposed to be x and y. Finally, we just want to return true if we exit this first for loop. So let's go ahead and submit this. So the time complexity of this algorithm is going to be O of n squared, and the reason why it is because within this for loop we have 2 nested for loops, so that means we have quadratic time complexity. One interesting thing that I want to note is the input size is always going to be a 9 by 9 matrix, so even though the time complexity of this algorithm is O of n squared, if we had a variable input, the input is always going to be constant. So this algorithm is always going to be in constant time. Another thing I want to note here is I do have 2 separate for loops here. However, you can just do all of this in one for loop. The reason why I separated it into 2 for loops is that it might be easier to understand for some people in this way.